I want to go and talk about periodic trends with you quickly. The assignment was due last week, and quite a few people didn't do it. Would have helped your test scores for sure. And then the metals and non-metals pre-lab questions. I want to talk about that with this class. And then we'll get started into electrons and ions and what you're supposed to do for tomorrow if there's power. So that's my plan. Somebody, okay. So I still don't see the same people. Okay, that is fine. So, Friday? I don't remember if it was Friday or not. I gave, it was a week ago Friday, I gave you this free lab. Have that tab open anymore. And about a dozen people, mostly in first and fifth period, gave me some interesting answers. And I just want to remind you that when you go online and get information that's not information that I've given you, you really should cite that source. So again, about a dozen people, mostly in first and fifth, told me that metals have a deep ringing sound when struck, and non-metals are non-sonorous. Perfectly legitimate, except I never said anything about sound. It's not in our background information, which is where I expected you to get those characteristics from. It's not in our notes, which we did in lecture. It's not in our textbook. So you got it from somewhere, and you really should, as part of that academic integrity thing that we talked about previously, you really should cite your source. And what else did I want to say? I think that's it. And then the other item was this one. So there's 7 of you that haven't done this. And this was the Google slide where you had to move things around. So you can get that done by 1:45. You can get full credit. I'm going to post the answers at 1:45 too. And if you turn it in after the answers, you won't get full credit. Okay, you only get half credit. So just FYI on that. Makeup test will be Thursday as my plan after school, because obviously tomorrow's going to be dicey, and Thursday might be too. We'll see how it goes, but that's my plan right now, is after school on Thursday to have everybody come together for the makeup test. Okay. There's a couple people in every period that need to make it up. Oh, except for first period, sorry. Okay, so I'm going to stop babbling. Well, a little bit. Here's what popped into your feed yesterday. My apologies, because many of you had power out, and I did too. I didn't go to the Ed Puzzle site and to Google Classroom, so some of you think this was due today. I'm impressed that you got this done already. Good job. I'll go through and scan that real quick for hero points. I should do that, huh? It's not due until Thursday because of the whole storm situation, okay? It's just a quick overview. I think it's under 4 minutes on ions. We're going to talk about that today too. This also went into your feed because I couldn't get it out, and I'm going to need it today. So this is a note sheet on Chapter 7, Section 1. And then I'll talk about the other things that showed up and what you're going to do with those for tomorrow's assignment, asynchronous assignment. So this is the paper, well, this is the Google Doc that you can follow along with with my PowerPoint. Does anybody have any questions about the lab, the Google Slides, the makeup test, any of the stuff I've been talking about?
Miss Scotches,
Yes, sir.
in Aries, I have a missing assignment on the test, but I took it on Friday.
Yeah, I sent you a message, Jalen. You should stay after class. We need to talk.
Okay.
Okay. Anybody else? All right. So with this at hand, or on your split screen, or have a piece of paper handy, whatever, I'm going to go through as much of the PowerPoint as I can and try and leave 8 to 10 minutes to go over the work for tomorrow, so it makes sense, hopefully, for you. Let's get rid of this, get rid of this. That's not what I need. Where are you, PowerPoint? Sorry. It's physics, don't need that. There it is. All right. So the substance here, probably some of you have seen around our area, because there's a fair amount of fool's gold in Sonora. It is a compound made from iron and sulfur, and it's an ionic compound. It is a metal with a nonmetal, and we'll learn more about what that all means in coming weeks. This is an interesting formation of it. The pyrite that I found on my property and in our creek is more cubic. You can sometimes find it in little things that look like flakes. I don't know if any of you have done gold panning before, but it sure is, wow, I'm going to be rich. Look at all that gold in my creek. That's not gold. It's just gold color. So it's a crystalline solid, and we're going to talk more about what that means and ionic compounds as we go through the class. But probably some of you have seen pyrite. I have some in my classroom because I kind of like to pick up rocks. You can probably see them, those of you in my classroom. I have a little mini geology fetish going on, so I love looking at this stuff. All right, what are valence electrons? Valence electrons are the electrons in the highest energy level, the highest occupied energy level of an atom that corresponds to the period that they're on. And the period that they're on, excuse me, I'm gonna make sure I'm not missing someone needing something. Okay, thank you, Maren. Glad you're here. So we've got a note sheet and a classroom, and I just started on notes. All right, here we go. Let's try it again. Valence electrons, highest occupied S and P orbital electrons. So some atoms only have S electrons, and some have S and P. So you have to pay attention. Whatever line or period the element's on is the highest occupied energy level. And the S and P orbital electrons are the valence electrons, and they're the ones that determine the chemical property of your element. Chemical properties are how they react, how they interact with other elements. Remember, valence electrons, these S and P, are at the highest energy level, so they're farthest from the nucleus, and they're the outermost layer. And so one atom's outer layer can encounter another atom's outer layer. And sometimes they steal electrons from each other. Sometimes they share electrons with each other. It just depends. And that is chemical properties and what we're going to be talking about the rest of the year. And valence electrons are easy to determine from the group numbers. Okay, now, with a caveat. So back in the old days when we used Roman numerals and the A thing for the representative elements, remember representative elements are the S and P block, the two S block columns and the 6 P block columns on the other side. Okay, those are the elements that we call representative because they best represent the periodic law, the trend of repeating patterns, and that has to do with their valence electrons. So the cool thing is, if you just look at their group number, That's their number of valence electrons. Except when you get to the new way of numbering 13 to 18, then you just have to kind of ignore the 10 and just go with 3 through 8. Okay. Everybody knows, I hope by now, that the last column, group 18 or 8A, which used to be Roman numeral 8A, those are the noble gases. They have their octet. They have S2P6. 2 plus 6 is 8 valence electrons, except helium, of course. Okay? They're all full. They don't have any room. They have what they need. They have their complement of valence electrons, and that makes them less reactive and more stable, and they don't form compounds. This gentleman, Gilbert, G.N. Lewis Gilbert, nothing Lewis, was pretty early on, he's responsible for the octet rule that we're going to talk about a lot. He explained the reason why elements formed compounds the way they did had to do with them forming octets of electrons, 8 valence electrons. And he said they're going to get stable like a noble gas if they have 2 and 6 S2P6. Unfortunately for him, he wasn't, I guess, very nice to other people, and they kind of made people mad. So he didn't get a Nobel Prize for his work, but he was pretty smart. He did a lot of other things as well, but the octet rule is what we're focusing on. All right, so dot diagrams, Lewis dot diagrams, how I learned it. Electron dot structures is how our book phrases it. They're just a way of visualizing on paper electrons as dots, valence electrons. Now, mind you, they're going to have other electrons underneath the valence electrons. Forgot to mention that's the other 2 periods this morning, but we're just talking about the outer ones. Okay, so if you imagine that the element symbol is the box, like it is on the my periodic table, go, oh, there it is, like this. You know, you got a little box and a symbol. You don't have to draw the box, but you can draw the box if you want to. If you just imagine a 4-sided box around the element symbol, each of those dots represents a valence electron. Okay? And when we're doing dot structures, right now it's not, it helps understanding why they form ions, but later it'll be really important to have this tool to predict chemical formulas. So lithium is in group 1, an alkali metal. It has 1 valence electron. Group 1, 1 valence electron. That means it gets 1 dot. Now, you could put the dot at 12 o'clock, at 3 o'clock, at 6 o'clock, at 9 o'clock. It doesn't matter. It really doesn't matter. Our book puts it over here at 3 o'clock. It's fine. It's irrelevant where you put it, okay? Just know that there's 4 sides. You don't, like I said, don't even have to draw the box. Okay. Group 2, guess what? They have 2 valence electrons. So they're in the second column of the S block. This time, it's a good idea. It's not absolutely critical, but it's a good idea to go ahead and put them on opposite sides. You can do top and bottom, that's fine, but put the dots on opposite sides of the element symbol. Now, normally you would think, oh, yeah, S, and then the 3 P's. You told us that the S has to fill before we start putting them in the P's. True. However, we're following the pattern like Wundt's rule, right? We're going to keep everybody to their own seat all the way through. I think I skipped that slide. There it is. I forgot to talk about it. So Wundt's rule, remember, is everybody's going to spread out as much as possible. So just visualize the atoms, valence electrons, as far apart as possible. Okay? And then for group 3, hopefully you can figure out they have 3. This is aluminum's family. And it's irrelevant whether you start at the top and then move around. I'll put the 3rd dot down at the bottom. It doesn't matter. Okay? That's 3 dots. Group 4, carbon's family, has 4 valence electrons. They bond 4 times, and that gives them unique properties. Of course, carbon's a nonmetal. Silicon and germanium are metalloids. This is not a picture of carbon. It's carbide steel, I'm guessing. Yeah, carbon is not a metal. So 5A is nitrogen's family, and they have 5 valence electrons. And so you'll notice pretty quick, you got 1, 2, 3, 4. Uh-oh, got to start doubling up. So this term, add this to your notes. I don't have it on the note sheet, but write this somewhere. This is what we call a lone pair. So these are electrons from this atom. Remember, nitrogen is on the second row. It ends in the third column of the P block. So it ends with 2s2, 2p3. 2 and 3 is 5. So it has 5 valence electrons, 5 dots. And that means there are 3 places that would like to have another electron. Okay, this one is all paired up, and this has an influence on molecular shape or geometry. And we're going to talk a lot more about that later. But if nitrogen could find 3 more electrons, it would end up having an octet, right? 2 and 3 plus 3 electrons gives you 8. The nitrogen ion, which is called nitride, will have a -3 charge. Or, we're not talking about ions, which we are right this moment, this electron could come, well, all the electrons are coming from another atom, but hydrogen only has 1 electron. So if hydrogen hangs out with nitrogen, we're going to end up making an H3. And this is ammonia. It is a gas at room temperature. The stuff that you buy in the store for a cleaning solution is water, usually with some soap suds, percolated through with the ammonia gas, and it makes something else that we're going to talk about quite a bit, ammonium. And anyhow, this introduction, this compound, figuring out how to make ammonia from nitrogen and hydrogen in the atmosphere was a huge deal. And we'll talk about how that got started in a couple of weeks. All right, group 6, oxygen's family. Hopefully by now you got this one figured out. It has 6 valence electrons. Kind of a weird concept. It has 2 lone pairs. They're not alone, there's 2 of them, but yeah. It also has a great influence on the shape of compounds with oxygen. And of course, oxygen needs just 2 more electrons to get its octet because it ends with S2P4. And if it gets 2 electrons, it's going to end up forming a -2 ion. It also can share electrons with hydrogen, of course, and you know this compound, I hope, H2O. Now, one thing I do want to say about, I forgot to say this also in first and second period. When I was talking about the dots, it didn't matter where you started and where you ended. It is important that you keep in mind that these lone pairs are side by side. Doesn't matter which 2 sides, but they should be side by side. Again, because it has a tremendous influence on molecular geometry, and we're going to talk a lot more about that going forward. Okay. Group 7, the halogens, of course, have 7 valence electrons. They just need 1 stinking more electron. Okay, so when fluorine grabs an electron from somebody, greedy fluorine, it ends up with that -1 charge. Remember, electrons are negative, and so the charge is going to be negative if you add an electron. Finally, then the noble gases have their 8 valence electrons all done. And I think, yeah, you have that diagram on your picture, on your note sheet. This is from our book, and they show the representative elements. Group A elements are the representative elements. This is the S block and the P block, the 2 sides of the periodic table. And if you look at this and look at the valence electrons again, it's 1, 2, 3, 4, 5, 6, 7, 8. You just skip those 10 D elements in the transition metals, okay? We're just ignoring that. So everybody in group 1, the alkali metals, everybody has 1 dot. That's how you do the dot diagrams for every alkali metal. Every alkaline earth metal has 2 dots. Every element in boron's family has 3 dots. Everybody in carbon's family gets 4 dots. Nitrogen's family, everyone has a lone pair and 5 dots. 6 for oxygen's family, 7 for the halogens. And of course, the Noah gases have 8, except helium only has 2. They represent it with like this to show that it's not going to find another electron to pair with. All right, so this is on the bottom of your table. And again, 1 valence electrons, 2 valence electrons. Forget about these guys for now. We'll have to talk more about them on Thursday. 3, 4, 5, 6, 7, 8 valence electrons. What do metals do with their valence electrons? Everybody should know that they lose them, right? Losers on the left. So these are all metals. It's easier for them to lose 1, 2, or 3 valence electrons. They can't pick up 7, 6, 5 electrons, or nuclei aren't big enough. Ignore carbon's family. And then over here, the nonmetals are going to gain valence electrons. To get 8, they have 5, they just need 3 more. They have 6, they just need 2 more. They have 7, they just need 1 more to get their octet. That also gives us some information about the type of ions that these elements will form. So what's an ion? An ion is a group of atoms, or a single atom, it can be, that have an overall charge. The reason why they have a charge, of course, has to do with their electrons and their protons not being equal. So if you lose electrons, you're going to have more protons. If you gain electrons, you're going to have more electrons. You're going to have a negative charge. If you lose electrons, you're going to have a positive charge. So sodium's element 11 and has 11 protons. The neutral sodium atom has 11 electrons. However, that last electron is all by itself in the outer layer. It goes bye-bye. Somebody steals it and takes it away, okay? That leaves 11 protons and 10 electrons, so it has a +1 charge. Oxygen has 6 valence electrons, okay? 8 protons. If it grabs 2 more electrons, it's going to end up with a -2 charge. Talked to you about this a ton already, so hopefully this isn't hard. Cations are positive, remember, and that's because the metal has lost an electron. Got my eye on you. Chemistry cat. Right. And so here's sodium again. 1s2, 2s2, 2p6, 3s1, 2 and 2 and 6 and 1. That's 11 electrons. It always has 11 protons. That doesn't change. We don't change the nucleus. If one of those electrons goes to somebody else, like chlorine, the leftover is 11 protons, 10 electrons. And 2 and 6, this electron went bye-bye. That leaves us with an octet in the outermost shell. Right? So what are they doing when they form ions then? Atoms are trying to get isoelectronic, that word, with a noble gas. And so here's our filling diagram, the old style stuff that we started when we were doing electron configurations for Christmas. 1s2, 2s2, 2p6, 3s1. If this 3s1 gets ripped off, then we have the sodium ion. It's missing its electron in the outer shell, the highest energy level, highest energy layer away from the nucleus. Guess what? Neon always has 10 electrons. It always has 10 protons, and it always has 10 electrons. And neon is a noble gas. It has 8 valence electrons. And by losing its 3s1 electron, sodium becomes isoelectronic with neon. So again, metals lose their valence electrons, right? Lose on the left. Okay. And that then takes them down to the next closest noble gas. Now remember, I'm trying to do this where I can see it. Sodium and neon are just one number apart. And you probably can't see that, right? Neon's 10, sodium's 11. So even though they look like they're far apart on the periodic table, if you think of it as a continuum, a whole string, 1 through 118, they're not that far apart. They're right next door. And again, they form cations. Again, you should know that already. Okay. Another way to draw it, right, with the dot diagram right here. Here's your 1 valence electron, whoop, no dot, and a +1 charge. The electron doesn't disappear. It doesn't vanish. It goes to another atom. They show pictures of sodium vapor lights. Skip this right now. Magnesium loses 2, right? Magnesium's in group 2. It has 2 valence electrons. They both go to somebody else, and you get the magnesium ion, the +2 charge. And there's magnesium in walnuts, in case you were wondering. So cations in group 1, +1. Cations in group 2, +2. Valence electrons 1, 2, 3. Ionic charge +1, +2, +3. Lose 1, lose 2, lose 3. And remember, they're positive because you're losing a negative. Negative times negative is positive. Cover tomorrow or Thursday, anions again, they gain electrons. Gotta hurry up. And so they're going to be more negative. The one thing that happens with anions as well, when you name them, they're monatomic. Mono means one. Poly means many. Monatomic means single atom, one atom. You change the ending to "ide" on the end. So you don't say chlorine, you say chloride, like sodium chloride. Sodium chloride. So this is a nitrogen ion, it's nitride. Phosphorus ion is phosphide. Arsenic ion, arsenide. Big one, oxygen isn't the oxygen ion, it's oxide. Okay. Chloride instead of chlorine, etc. Fluoride, chloride, bromide, iodine. Halogens are the most important nonmetals, the most reactive. They just need one more electron, so they're going to grab it from just about anybody, right? Here's 2 and 5. That's 7 valence electrons for chlorine. Grab one more sodium, and you've got yourself a chloride ion, and now it's 2 and 6. It has its octet just like argon always does. Okay, so the chloride ion is isoelectronic with the argon atom. I'm going to stop this because I am not paying attention to the time very well. Questions? I want to show you tomorrow's assignment. Any questions? All right, let's hop to this. This is in your classwork feed. It says sorting ions, monatomic ions. It asks you to define what an ion is and what a monatomic ion. And then it has 2 examples placed in different boxes. So you're going to sort them based on their charge, positive or negative, +1, -1, as well as +1, +2, +3, +4. And the list you're going to look at is right, wait for it, here. And these are common ions. It looks like a tremendously intimidating list. Most of the monatomic ions you can figure out just by their position on the periodic table, like we've been talking about. And again, we're going to revisit this. There's a whole bunch of polyatomic ions on the right-hand side of this document. So let me go to the out of this in. Just want to point out 1 or 2 things really fast. I think I could do it. I think I can. So here's the list. H plus is the hydrogen ion. So when you go to this box, it's already in there as your example. You write the symbol for the element, the charge of the ion, and the name of the ion, just like it is on the list. The next one on the list, number 2, is NH4. That looks a lot like the compound I showed you, except it has an extra hydrogen. We'll learn why that is later. But capital letters mean that's a different element. That means it's polyatomic, plus the subscript means it's polyatomic. Okay, this has actually 5 atoms stuck together. That's not what you're doing today. Okay, that's on Thursday. We'll talk about the polys. So you wouldn't write this one. The next one you would put on your list is lithium. And so you would write Li or type plus, remember, capital letters with a lowercase letter, that's the symbol for lithium. So when you see 2 capital letters like this one, that's a polyatomic. That's a carbon with a nitrogen atom. Okay, not doing those today. Lithium is an element, has a +1 charge. Metals go by their name. Next one, sodium, that would go in the same box. Potassium would go in the same box. Silver would go in the same box. Skip the mercury ones for now. Copper can be a +1 and copper can be a +2. So for example, Cu, big C, little u, 2+, that's the copper Roman numeral 2 ion. And I'll tell you why they're named like that on Thursday as well. Notice that hydrogen can also have a negative charge because it can also pick up an electron. Remember, hydrogen has 1. It can actually get its second one, and then it's isoelectronic with helium, and that's the hydride ion. So you just work your way through the first 2 lists. So like hydronium, that's a poly. Hydroxide's a poly. Cyanide's a poly. Fluoride's a poly. Almost everything after nitride is a poly except for this one. So you just want to catch the phosphide is there on the list. All the others you save, and you're just putting them in the correct charge box. Normally you do this by hand. We make flashcard necklaces and all sorts of silly things. If it wasn't what it is. So I hope that makes sense. I'll stick around for a couple minutes. If it doesn't, ask me any questions.